Hello Year 11, this is the second required practical in the forces unit, or the first depending on which way you look at it. This one is about the spring, and it's required practical 18. Investigate the relationship between force and extension for a spring, a nice easy short one. This could be classed as Hooke's law practical, based around Hooke's law, and the Hooke's law formula that we're going to look at is F equals KE, and we'll come back to that in a minute. Right, so the equipment we're going to use here is a spring, which is what it says, force and extension in a spring. A spring looks like this. You should know through general life what a spring looks like. It pulls, it returns back to its original shape, but they have original lengths. Now the original length of that spring would be that long, and the original length of that spring would be that long. Now importantly, the extension on both of those is 0. So at the minute these are extended 0. However, we're looking in this score because Mr. Bowden has made this spring reach 0 there, so we can directly read the extension off. Point to note here is, if you were to look at the spring like so, that does not look like it's at 0. If we were to look at it like that, that does not look like it's at 0. What we must do whenever we're reading the spring is we must look at it parallel. That reduces what's called a parallax error. And this is the big one for this practical, because what that means is if that's your eye, that's your eye, and that's your eye, here is the item and here is the scale, then there's your true representation. If we look from above, there is a false representation, and there is a false representation there. So whenever you're doing this kind of experiment, and if it asks you for what kind of error could happen here, parallax error would be a good one. So again, we've got to be careful about what we're talking in terms of terminology. This is a mass, this is not a force. When it is applied by gravity, it becomes a force. Each one of these is 50 grams, that's 0.05 kilograms, which means that each one of these is 0.5 newtons. W equals m times g. Half a newton, 1 newton, and so on and so forth. Once again, I've got a results table where I've got force, the independent variable on the left. The independent variable is the one you change, or I, independent, I change there. And the dependent variable always goes on the right. I have used what the quantity is and what the unit is. What the quantity is, what the unit is. So we're going to start with 0, and what I said earlier, when there's a spring has 0 load, it has 0 extension. Then we're going to go up in 0.5s. You can see the interval. The interval is the steps between each one. That is a nice steady interval, appropriate interval. The range would be 0 to 3 in this case. So let's get on with the practical. If I load the hook on the spring, then there is a tendency for the spring to bounce. This is where you cannot read the bouncing spring, so you must damp it slightly with your finger, and then you are okay to read it. That is now at roughly 1 centimetre. If I load it again and damp it, don't let it bounce. That's about 2.5. Load it again. .5. Load it again. 6. Load it again. 8, and load it again. 10. Here are my results. This is the force, this is the extension. Now these aren't ideal. What we would be expecting here would be equal steps proportionality, but that's not what the data says, so we've got to go with what the practical says. What we would expect though is a straight line that goes through there, those points. And if we were to draw a gradient triangle there, we would have delta F over delta E. Now, looking at that formula from earlier, F equals KE. So therefore, if we drop the E down here, we have F over E, which will leave us with K. Now, K is the spring constant. K tells us how stiff the spring is, and it will be in newtons per centimetre in this case. You would work that out by getting these steps here. This is only a sketch graph, dividing it by this distance here, and that would give you the spring stiffness. Okay? So once again, don't forget to say what measurements you're taking, what equipment you're using to do them, the formulas that you use, the intervals and the errors that may come up. Don't forget, if we did repeats, the uncertainty, and this came up in paper 1, the uncertainty is the range of results divided by 2, plus or minus.